In this last experiment, we're going to see the response of our control system to disturbances. Specifically, if I apply some constant disturbance of value, let's say 5 volt as an input to the plant, then does the steady state speed still reach the value of 12 or not? Now, this disturbances basically mean the inputs which are also acting on the plant and we have no control over them. See, if we knew what the disturbance was, what that extraneous input to the plant was, we can just correct for it. We can apply the corresponding volt, we can apply 5 volt less. But the real problem is we don't know what the disturbance is. But can we still design the control system to cancel the effect of the disturbance? And the answer is yes. But we may need to know something about the disturbance. For example, in this case, the theory says that if the disturbance is constant or constant-ish, then having an integrator specifically in the controller will get rid of the error in the steady state due to the disturbance. So having an integral in the controller actually helps you get rid of the effect of step disturbances. Okay, now is it a realistic situation? Well, that was explained in the beginning section over here. That if you consider an autonomous vehicle, and then if there's a constant force acting on the autonomous vehicle, and where could that constant force be coming from? Well, one example is the vehicle is actually on a slope. So you're doing a cruise controller of a vehicle and you design the controller like this on a flat ground. But if the ground has a slope, then there's a component of the gravity, a constant component of the gravity acting down if the slope is constant. So there we go, an example of a constant force acting on system. Other options could be, let's say there's a wind and the wind is applying a constant-ish force on the vehicle. So as long as there's a constant-ish force acting on the vehicle, if you write down the equations, that would come just like this constant friction force term, there'll be another term. And just like that constant friction term, that other constant term would get absorbed into VA. So effectively, and the math shows that having a constant force acting on a vehicle is equivalent to just giving a constant voltage for this setup. So that's why this is not some like, make believe unrealistic situation. Giving a constant voltage disturbance is equivalent to something realistic. Okay, now how do we implement this? Well, that's really simple. All I'm going to say is that the voltage that goes to the plant from my setup is whatever the controller says plus 5. I'm just calling it 5, but in real life, you would not know if it is 5 or not. And the code for that is really simple. You have your controller code already, and in this controller code, you calculate the voltage over here. And right after that, you can say, oh, your voltage is actually whatever you think the voltage is from the controller plus 5. And then that gets converted into a DAC value. Okay, there we go. We have applied a disturbance. We already know from theoretical analysis that having an integrator in control is going to get rid of the disturbance, but let's test it out on real life. Okay, so I'm going to plug my Arduino in and it's running because of the previous code. So we're going to just upload this. Let's see how it goes. Uploading, done uploading, serial monitor, 1, 2, 3, okay. Here we go, pretty quickly, it achieved the speed of 12. So despite the presence of this extra disturbance, the integral action helps you reject the disturbance. And you can take this data and then save it in an experiment number 2 data file. Make sure that the last line and the first line are good. Okay, so nice. And then we can actually simulate the theoretical versus experimental response. Now remember, this response is we are both giving a reference command of 12 and there's a pre-filter over there and the whole controller. And also we're giving a disturbance. So we're doing the response of the system to two inputs, the reference command and the disturbance. Sadly, systool cannot do it. Systool can only do one response at a time. It can give you the response of output from the reference command. It can give you the response of the output from the disturbance. Like if you do the step response of a transfer function from R to U, you'll get the response to R. If you do the step response of the transfer function from du, remember the disturbance to the input of the plant was called du. So if you find the transfer function from du to y and do the response, you'll get a disturbance response. But we want the sum or the combination of those two. Tool can't do that, so we have to do it in MATLAB. Okay, so let's see. I'm going to open up the MATLAB code over here, and this is lab 5 experiment number 2 data text desired speed, the voltage disturbance, the controller transfer function was 1 plus 20 over s. Is it? I guess yes. And then the pre-filter filter transfer function was equal to 1 divided by 0.02 times s plus 1. Great. And then type the value of DC gain of the motor and tau value, and then those values. Great. And then see, we're doing two simulations. Simulation of the closed loop system to the reference command, and we of course going to have to multiply the pre-filter transfer function over here, and the simulation of the transfer function from disturbance to the output multiplied by the disturbance. And then we're going to plot the response we got from the experiment, t and omega, which you got from the data, and the total of the two responses. Okay, let me explain, briefly how this mathematically is functioning in case this is not clear. Okay, let's annotate over here. So this is my system. There's a G, there's a K, and then input to the G is both the disturbance, which we call as du, and the input from the and output of the controller. No H, but there is a pre-filter to the reference command. So the output of this system, the output y, there are two real inputs to the system. One is the du and one is r. These are flowing out of thin air into the system, as in thin air, as in we decide them. Every other signal in the system is interconnected. Okay, so the output y is going to be something multiplied by the reference command, something multiplied by du. If you try to do the algebra, y, the output, is equal to g times this signal. This is u plus du. U is equal to k times this signal. That signal is this minus this. That is r times f. This is equal to y. If you rearrange all that, you're going to get this format, that y is something times the first overall input plus something times overall. This something is called the transfer function from r to y. This something is a transfer function from du to y. And if you use the Mason's rule, the forward path from r to y is fkg divided by 1 plus the loop transfer function, which is just gk multiplied by r. Similarly, the forward path from du to y is just g, when you're going to go from directly from du to y, divided by 1 plus the loop transfer function, which is gk multiplied by du. So we have to do the response of both this transfer function with that input and that transfer function with this input, and then add the two responses up. And that's precisely what we are doing over here. Okay. All right, let's see how this looks like. Where's my run button? Right here. Oh, syntax error. Line 20, column 29. Semicolon, please. Busy, busy, busy. All right, there we go. So there is some warning over here, but I'm going to ignore it as long as it's not an error. But let's just have a look at the warning anyway. That's new. Okay, so this is the experimental response, the blue, and the theoretical one is green. Yes, there's a difference of about, let's see how much is 13.29, and this is 12.2. So there's a difference about 1 radian each per second. That's an error. I'm going to chalk this up to the modeling errors that we have, especially when we deviate away from the 12 too much. Most of our calculations were done around 12. On all our calibrations were done around 12. So when we deviate away from it, don't expect to match too closely, especially that the conversion from the DAC value to the voltage, that thing was, that thing goes off as you go away from 12, if you remember the graph. Okay, but anyway, there we go. The real thing is that the effect of the disturbance was cancelled, even though the settling time and the overshoot of the system has changed, the disturbance, but the still system reaches a speed of 12. And that is your experiment number 2. So this concludes the 5 lab series. Hope you learned something. These are pretty useful controller design techniques. And remember the controller design process. You model your system and then design the controller in the simulation. And then if you do your modeling properly ish, whatever controller you design in the simulation, you can just directly plug and play into the actual Arduino and it works. Otherwise, if you do not do any modeling and sysitol and theoretical stuff, you will be spending hours and hours tuning those gains. Okay, so that's a beauty of understanding things from a theoretical perspective. Okay, so hope you enjoyed it. Have a nice time.